My name is Patrick O'Reilly, and today I'll be presenting the work Code Drift towards Idempotent Neural Audio Codecs. This research was supported by NSF Award number 2222369 and done in collaboration with Adobe, with co-authors Prem Sitharaman, Jiaxi Su, Seiyu Jin, and Brian Pardo. Listening examples can be found on the supplementary web page linked to by this QR code. Neural audio codecs encode audio signals as low-rate sequences of discrete tokens, which can then be decoded to reconstruct high-fidelity audio. The comparatively small size of these token sequences facilitates efficient storage and transmission of audio at low bit rates while maintaining high perceptual quality. Additionally, generative models can be trained on these compressed token representations rather than raw audio. In this sense, neural audio codecs are analogous to tokenizers used to map data from modalities such as text to token representations amenable to generative modeling. However, compared to text tokenizers, which map language to tokens at a rate of around 1 token per word, neural audio codecs are much more fine-grained in order to capture perceptually relevant details. For instance, current neural audio codecs might map a short speech recording to hundreds of tokens. We find that unlike text tokens, these fine-grained audio token representations are largely non-idempotent. If we decode tokens to audio and re-encode to get tokens again, these new tokens will often differ from the original tokens substantially. For some neural audio codecs, 70% or more of tokens may change. This means that language model-style watermarking methods, which influence and detect token selections, cannot be easily applied to audio generative models. The instability of these token representations under repeated rounds of encoding and decoding also has implications for the deployment of neural audio codecs in real-world applications. For instance, an audio file may be repeatedly encoded and decoded with a codec for compression or retargeting. We find that the instability of neural audio codec tokenizations can result in significant degradation of audio quality under multiple rounds of encoding and decoding, potentially limiting their usefulness in such scenarios. To address this instability, we propose a method for encouraging idempotent token mappings by fine-tuning neural codecs with an additional training objective. Our method produces more stable tokenizations than any existing neural audio codec without sacrificing audio quality or downstream generative modeling performance. We next describe our method. Neural audio codecs typically encode signals as continuous, time-varying features using a deep neural network we call the encoder, then quantize these features to a learned codebook of templates, and finally decode quantized features back to audio with a deep neural network we call a decoder. To simulate multiple encoding and decoding passes, we re-encode decoded audio and explore 3 loss functions that penalize the distance between feature representations obtained in the first and second encodings. These include a loss on the continuous features produced by the encoder, L sub ENC, a loss on the factorized projections of these features prior to quantization, L sub PROJ, and a loss penalizing the distance between quantized projected features from the first encoding pass and unquantized projected features from the second encoding pass, called L sub CODE. In our experiments fine-tuning a reproduction of Descript audio codec with each of these objectives, we find that the third, L sub CODE, performs best in encouraging idempotent token mappings. Our fine-tuned codec model preserves audio quality significantly better than the base codec after multiple encodings. Moreover, our idempotent fine-tuning does not compromise desirable distributional properties of the encoded token representations, preserving codebook entropy and downstream generative modeling performance as evaluated through an MFCC vocoding task. Through this work, we hope to draw attention to the non-idempotence of existing neural audio codecs and to encourage future work improving the stability of audio token representations. Listening examples can be found at the website linked to by this QR code. Thank you for your time.